So another cause of autocorrelation within regression then is this model specification error. So a model specification error occurs if important variables that should be included in the model are excluded, or if the model has a wrong functional form. In either case, the setup of the model is incorrect or misspecified. So it says here in the middle that specification errors mean that it is important to consider financial or economic theory and or other relevant academic literature, so that any mathematics and statistics that you use is only part of the story. And this is the bit I wanted to emphasize in this lecture. So the thing to make sure you do as part of MSc dissertations is to try and base things on the relevant academic literature if you're not sure, so that again the emphasis here is on communication and that people can track your thought processes back to referencing the established academic literature. So as far as today is concerned, specification errors mean that residuals from an incorrectly fitted model may exhibit a systematic pattern, and as part of this, what you often see, rather than a purely random pattern, is some autocorrelation in the residuals. And then it says here that a commonly encountered example to account for the lagged effects of economic variables. So variables that occurred, say, last week, so perhaps last week's stock price still has an impact on today. This would be a lagged economic variable. Another example within complex economic networks is this cobweb phenomenon. This is commonly encountered in the context of agricultural commodities. So economic agents like farmers commonly base decisions on the prevailing price from last year when deciding how many goods to supply to the market next year. So for instance, the price has this sort of functional form here. So the idea would be that if the price is high in the previous year, there'll then be a sort of more supply to the market the subsequent year. And then the result of this is that the disturbances in this equation are unlikely to be completely random and patternless, precisely because they represent the actions of intelligent economic agents, in this case farmers. So the net result of this would be that you have patterns in the regression residuals, and as part of that, autocorrelation. And then this is the thing I wanted to sort of emphasize here, is that there's a wider economic theme that's important here. Financial and economic variables always represent the collective investment decisions of many different people, so will often be inherently more complicated than the mathematical and statistical tools used to describe them. So I think there's a sort of all sorts of contemporary examples of this. So an example might be if you close pubs at 10 o'clock, you then get unanticipated clustering of people outside the pubs that close at precisely 10 o'clock. Another example of something that can cause autocorrelation is data manipulation. So if you have some sort of artificial smoothing, so for example, if you look at quarterly data, this might smooth out some of the wild fluctuations typically seen in more granular monthly sales figures. Let's see, for instance, examples where census and economic survey data may be interpolated. Now, this is in some sense just an unavoidable consequence of data being imperfect. You might have, marked constraints in terms of that's available in social science applications. So there's nothing you can perhaps do about this sort of quality issues, but they may induce systematic patterns, and as part of that, autocorrelations into the disturbances of a regression model. Okay, so there's no magic solution here, but this remains an important consideration throughout. So in this case, just a sort of imperfection of the data set and what data is available, often these sort of smoothing methods may induce an artificial autocorrelation in the data that you see. Okay, not necessarily an obvious solution to this, but it's important to be aware that this is a common problem that can occur. In terms of the detection of autocorrelation, then, there are two possible methods. So graphical methods and statistical methods. So graphical methods might be more simple, but they can be more robust on occasion and more informative in applied project work. Statistical tests, so this is a sort of natural thing you might expect to sort of see on a lecture course with an exam. So testing formal hypotheses with precise numerical answers, things like the runs test and the Durbin-Watson test. And I think the thing to sort of guys here is that probably at an exam, I'd be more likely to set something like a runs test or Durbin-Watson test. But in terms of this course, probably you would need both. Certainly, it would be a good idea to try and use both for practical projects and for dissertation work. And I think I've not always had the maturity and the experience and the training to appreciate this fully. But I think my advice now would be, in practical project work, try and use graphical and statistical methods as a cross-check of each other. So what you're always doing when you've got a practical problem is looking for two independent pieces of information that tell you the same thing. If they tell you the same thing, then this gives you a good indication that you're probably correct and you haven't made an obvious mistake. Okay, so though it may sound trivial, look for a combination here of graphical and statistical information. So the graphical tests for autocorrelation that I wanted to cover then. First one is a sort of time series of residuals, and the second one is an autocorrelation plot. So for the time series of residuals, all you do is you plot the residuals over time, and what you're looking for here is any evidence of a systematic pattern. So hidden amongst the maths of the classical linear regression model is the assumption of no correlation in the residuals, and you would expect, if you see the plot of the residuals of a correctly specified regression model, there shouldn't be any pattern over time in this time series plot. Now the second option here is this autocorrelation plot. So it's natural to think that successive residuals may be correlated. It says there natural to think that UT and UT-1 may be correlated. So in the context of the gold price and stock price example, perhaps the residuals for the year 2000 and 2001 might be correlated because they're right next to each other, and what you residuals at time t against the residuals at time t minus 1, and this has the added advantage of you can sometimes see a positive autocorrelation in this plot between successive residuals, so it can be clearer in this sense as to what is actually going on. So in this gold price to stock price example, so just to repeat the steps in terms of reading the data into R, so the data is this in this on canvas. So the best thing to do is to save this onto a USB stick and then read in the data using this command here. The read.table command provides the file path in commas, and you need to make sure you get the drive right here. So in my computer, my USB drive is drive E. This might be slightly different on your computer, which means that if you're doing this on your own laptop, it's possibly to the read.table command. The dataset contains two columns, the real gold price on the left and the real stock price on the right. And then what you would do here, once you've called this something simple and logical here, data 1, you call the real gold price in the first column, and that is what this first command at the bottom means. And the real stock price will be the second column of the 1 dataset. Okay, and it's really important that the data 1, you assign this thing here in the table command, matches exactly with the one used in the two lines of code right at the bottom of the slide. Okay, these two names need to match. If they don't match, R doesn't know what you're asking it to do. Remember, R is like a robot, simultaneously very clever, very stupid. So the way that the graphical tests for autocorrelation in R work then, so you fit the regression model, time series plot of the individuals produced. So you fit the regression model, so do the computation and call it something here. I've just called it model, so something as simple and logically named. Then once you've named it something, you can extract the residuals. Okay, to do which is what you call it, and then the dollar visit extracts the residual part of this regression model. And then the next command the residuals, and then you need to work out the length of this residual column, and then this then at the bottom slide, what that does is add a horizontal line at 0. Now the reason for that, as we show you in a couple of slides time, is if you do this, this gives you a horizontal line at 0, and the idea is that if the regression model is correctly specified, it is a 50-50 coin toss at each step as to whether the residual is positive or negative, and if you have this line at 0, it's possible for you to identify runs of successive residuals that are either positive or negative. So it does aid in the interpretation of the graph produced. Now, what you have to do in eViews then, so the regression, this thing here, quick estimate equation, and then we'll see the stop price, this is the y variable, and then the x variable, click OK. You then residual series as follows, so make residual series, essentially you just have to click OK at this point and it should work. And then got the residual series, what you have to do is then graph residual 1, which is again match the name of the residual series exactly to select part. Okay, so what you should see here is that the graphs in eViews are more of a sort of passive menu driven process, okay, but you're going to see examples later in this lecture where, because R is a high level programming language, it actually makes some of these graphs easier. So for this simplest example, you haven't quite seen yet that graphics in eViews is harder than in R, but for anything that's slightly more complex, you're going to run into the limits of what eViews is capable of doing easily, and R will become much better precisely because R is a high level programming language. So whichever of eViews or R you use to do this autocorrelation plot, you should have something like this, and this is an example of I've used R to produce. And to see here, you've got a horizontal line 0 to try and aid in the interpretation. Now it says there rather confidently that the time series plot suggests some evidence for autocorrelation. Now in part these are a little bit like trying to read some of these tea leaves, okay, but the thing to sort of watch for here is if you have successive runs of residuals either side of the line. So the idea is that it's a toss whether these residuals are positive or negative if you've correctly specified the model. And what you might have if you've got instead autocorrelation in the residuals is successive runs of residuals either side of the line. So if you look into index 6, a wad of observations that are all below the horizontal line at 0, this would count as a large run of residuals that are all negative, so this would give you some indication that you have autocorrelation in the residuals. And I guess the thing to sort of look for here is because the data is collected over time, as is the case with many finance and accounting data sets, this naturally leads you to expect to find autocorrelation. So another alternative is an autocorrelation plot of residuals. Now it's perhaps a little fiddlier to do, but this can at the same time be easier to interpret. So what is going on here is that autocorrelation just means correlated with itself. So it's natural to expect adjacent residuals to be correlated with each other. So again, if we look back at this example with the inflation adjusted gold price and the inflation adjusted stock price, it's natural to expect, for instance, some correlation between the residual for year 2000 and the residual for year 2001. So how you bring this out graphically is if you plot the lag 0 residuals against the lag 1 residuals, you'd expect to find a positive correlation. And then this is, I think, the first example of where R is beginning to do a better job than eViews. Okay, so if you think eViews is much easier than R when you first start, this is when the balance begins to shift in the other direction. Precisely because it's a higher level programming language, this begins to get easier to do in R than in eViews. Okay, and if graphics are starting to get easier in R at this point. This is going to be increasingly true as the subject develops.